Let's discuss equilibrium of a particle, where we will learn about free body diagrams in the context of systems that lie in a single plane, so where everything is coplanar, everything shares the same plane. After today's lecture, you should be able to draw a free body diagram, which is really, really important, and apply the equations of equilibrium to solve a two-dimensional problem. Now, we're not going to start off with bodies, we're going to start off with particles because they're a bit simpler and we can sort of step our way up in our learning and not jump too far. Normally in class, I would go through some concept questions, some example problems perhaps in the slides, although I typically have my own example problems at work. Since we're not in class, the quizzes will be online, and of course the examples, you should get the slides, you should go through those examples, which of course I'm skipping those particular slides. So you should go to the course site, get the slides, look at the questions and the group solving problems, the examples, all those things, and consider your answers and how you would approach those things so you can learn more. So what applications do we have for this part of the course? Well, we've got a crane here lifting a load. Now let's assume that the cable or chain or whatever it is the crane is using is fine. We know it won't break. But there are some straps that connect from a central point, a central lifting point, out to the barrel or whatever it is, maybe it looks kind of like a wheelbarrow that's being raised. Now this is probably not a wheelbarrow you would push around by hand. This is probably something holding, maybe half of a concrete truck's worth of concrete. This is a very significant load. How would you figure out how big the straps ought to be? Because hopefully your intuition is strong enough to realize that if the angle of those straps decreases, where they're more parallel, there will actually be less tension in them. But as you decrease the angle, as they go more and more towards the same, towards a collinear situation, the tension in the straps themselves will go up. So how do you determine the force in those straps? Well, obviously this is not a coplanar situation. This is actually a three-dimensional situation, but you can imagine a coplanar situation with just two straps rather than three. Of course, the bucket wouldn't necessarily be balanced, but we have to walk before we can run. Here's another application where a heavy load is also being lifted. You definitely don't want this dropped on your head. You don't want to be anywhere near this thing when it's being lifted in case something breaks. But how would you make sure it's not being broken? How would you make sure that the load is securely raised and held and then used as necessary? Well, notice that member AC and AB would need to be sized appropriately. And somehow you've got to find the force in that cable. Now let's just assume you know the weight of the spool that's being held by this rigging. If you know that weight, then you know how hard the crane is pulling up at point D on the entire spool and rigging assembly, just neglecting the weight of the rigging, which is cables AB, AC, and the spreader bar between B and C. But you don't know how much force is actually in AB and AC, and you might say, well, give me the weight of the spool, divide it by 2, and that's the tension in AB and AC. That's not correct. Actually, there is more tension in AB and AC than just half the weight of the spool. Similarly, with what you're learning, you can determine the force in the spreader bar to make sure that it won't fail as well. So applications of this part of the course are endless. So what about the ring itself? What about the ring at A? Well, there's tension pulling up. Now the tension TD, that force indicated in the figure with the coordinate system, would certainly be equal to the weight of the spool being held. But TB and TC would be the tension in cable AB and AC respectively, and we'd like to know the magnitude of those two forces so that the cabling assigned for AB and AC will be adequate to support whatever load it experiences. Another application might be the bridle portion of the cable used to tow a boat. So you see a bridle there, A, B, BC, BD. It's really BC, BD that is the bridle portion. And the amount of towing force, the 50 kilonewtons, will be spread out between BC and BD. Now here's the interesting thing. If you add the force in cable BC and the force in cable BD, you will find that they are actually larger than 50 kilonewtons, and that may seem a little bit strange to you. But force is not a conserved quantity. If the tow rope was attached at a single point up to the ship, then obviously the force along the entire length would simply be 50 kilonewtons. But force can be made from nothing. Force can be reactions. Force can be multiplied. You've probably used a pry bar before where you multiplied the force from one of your body parts, probably an arm or something, maybe a leg, in order to move some larger load. Or you could stand on the short end of a lever, have someone else operate the long end, and move your body's weight. So force is not something that is conserved, and it shouldn't be a surprise that the force in BC and BD are unknown and not simply half of the 50 kilonewtons. But we have to know the force in those bridle portions of the cable. Otherwise, we won't be able to size the cable correctly. So let's consider a very simple coplanar force system. So we've got a weight that is attached to a ring at A, and then we've got two cables from A to D and A to B holding this weight in equilibrium. We're assuming that this is in a vertical plane, so the weight is simply hanging down under the influence of gravity. Now the weight is not 40 kilograms, that's the mass of the object. To calculate the weight on the object, you would have to multiply the mass by the acceleration of gravity. So to determine the tensions in the cable, we will have to make something called a free body diagram. And how would you do that? Well, step one, you got to figure out what you want to be your free body. What is it that you're going to say, okay, this body is sitting here, it's not moving, and the reason it's not moving is because whatever forces are acting on it are completely perfectly balanced. Okay. Now, free body diagrams are absolutely critical. You'll see them in dynamics. You'll see them in other courses besides this as well. And so you need to get used to them. It takes a lot of practice to know what are the valid assumptions that go into a free body diagram, but you need to practice with it, and I've got example problems to help you. I also put a link on the course website that you should follow that helps you practice free body diagrams. So please definitely look into that, because one of the biggest problems students have in statics and in dynamics, quite frankly, is drawing a correct free body diagram with all forces present and in the correct direction. So this is a really, really important part of the course. So what exactly is a free body diagram? Well, it is simply a drawing that shows, in our case, not necessarily a body of size, but a particle with all the external forces acting on it. Now be careful, that's really, really important. We want to draw forces acting on the body, not forces that the body exerts on other things, but forces acting on the body. Okay, and in this case, the body is simply a particle, a point, okay, or something small enough that we can assume it is essentially a point. Okay, so that's what a free body diagram is. It is a drawing showing all of the forces that are acting on the free body. Because you see, it's that combination of forces that must balance out, because the particle is in equilibrium. It's not accelerating, therefore the forces on it must be balanced, you see. Why do we need it? Well, it's really the key to writing what we call the equations of equilibrium. It's the key to recognizing the correct forces and then calculating the magnitudes of those forces. If you get one force wrong, your results are going to be wrong. Now, sometimes we will neglect small forces, and that's okay. But you have to make a decision based on experience about whether or not you should do that. So this will allow us, writing the equations of equilibrium based on the free body diagram, will allow us to calculate the forces, or the unknown forces, acting on a body. Typically you have one or two known forces on a body, and you have all others that need to be computed. And the free body diagram and then the subsequent equations of equilibrium are the keys to calculating those unknown forces. So how do we do this? Number one, figure out which body you want to be the free body. Okay, so we're going to isolate that body. We're going to basically cut it free from all its surroundings. And in the example we're using, we're going to select the ring itself, which is called body A. Then we're going to show all of the forces that act on that particle. Again, you won't always know the direction of forces, but in this case, we do. So for example, the weight of the cylinder pulls on the cable between AC, and therefore there is a force on the ring A acting downward equal to the weight of cylinder C. Okay? Now, the weight of cylinder C, once more, is not 40 kilograms. It is 40 kilograms times 9.81 meters per second squared, which will give us a number in newtons. It'll be about 400 newtons, but not exactly, a little less, because 9.81 is not quite 10. So you've got to show all the forces. But wait a second, there are two cables attached to the ring. There's a cable at 30 degrees going towards B, and there's a cable horizontal going towards D. Since cables cannot be pushed, they can only be pulled, right? They're only in tension. You can't compress a cable without guiding its sides, and that's not what's going on here. Since that's the case, we know that the direction of the force acting on the ring from the cables must be pulling on the ring, you see? Because, you see, the ring is pulling in an equal and opposite direction and opposite magnitude to cable AB. And, of course, cable AB is being stretched by the ring. Okay, it's being pulled on. Now, we're assuming that there's no deflection of the cable. But the point is there are three forces acting on the ring, which we've called body A. One cable's pulling to the left, another cable's pulling up and to the right, and the weight from the cylinder is pulling down on that ring. And apparently these three forces are in equilibrium. Somehow you got to add them up, and the sum is zero because this ring, we know, is not accelerating. Now, there are active forces. Those are forces that are applied that are trying to move the particle, and there are also reactive forces. Reactive forces are forces that can actually vary in magnitude. So, for example, you notice the blue arrow is drawn in a different color than the two red. Why is that? Well, it's because the weight of the cylinder is a constant thing, right? It's not as if we're going to take this thing far away from Earth and the weight of the cylinder goes down. The weight of the cylinder, I don't care if you're on the International Space Station, that's actually not very far from the Earth, and the acceleration of gravity is about the same there as it is on the surface of the Earth. Although people think you're weightless up there, you're actually not. You're just in free fall. Anyway, the weight from that cylinder is a constant weight. It doesn't change. However, the force in the cables are reactive forces. If we disconnect the weight from the ring, there would be theoretically zero force in the cables. You wouldn't need any force in the cables. And so by attaching the weight, the force in the cables actually goes up to whatever is necessary to hold ring A in equilibrium, which is really interesting. So the force in the cables, these are reactive forces. So we've identified all the forces. We need to show, where we know and where we don't know magnitudes. If you have direction, that's really important because force is a vector and the direction is just as important as the magnitude. And so we've got to show as much information as possible. We've identified the forces, but now we need to jot down as much information as we can. For example, the force from the weight, Fc, was calculated by taking 40 kilograms and multiplying it by 9.81 meters per second squared to get the force in the cable from the weight C, or from the cylinder C. And then there is force in the cable going off to the left. We'll simply call that Fd. We know its direction, but we don't know its magnitude. And the force in cable AB has, again, a known direction, but unknown magnitude. Okay. Now what? Well, what are the equations of two-dimensional equilibrium? Well, they're pretty simple. It's simply the idea that the sum of the forces on the free body must be zero because the body is not accelerating. The body is not changing its speed. It's not starting to move. Therefore, all of the forces acting on this body must come out to zero. So FB plus FC plus FD must sum to zero. Now notice that equation is a vector equation. So in reality, since we're in two dimensions, that's two equations for the price of one. We've got an equation in the horizontal direction and another equation in the vertical direction. So basically the sum of the forces on this ring must come out to zero. Now, for any particle that's in equilibrium, the sum of the forces acting on it must be zero. All forces added together on that particle must come out to zero. Or in other words, if we look at the components of that equation, the horizontal component forces must balance and the vertical components of forces must balance. And that's what the last equation there says. If we write this in scalar form, basically we get two equations for it, and that is, or from it. That is, that the sum of the forces in the horizontal direction equals zero, and the sum of all the forces in the vertical direction equals zero. You might say, okay, that works just fine for the weight and for FD, in other words, FC and FD, but what about FB? It's not in the vertical or horizontal. Well, what you have to do there is take the components of FB. FB certainly has a horizontal component, the horizontal component of FB would belong in the sum of forces in the x direction equation, and the vertical component of FB, the y component, would belong in the sum of forces in the y direction. So then we have two equations, and we have enough then to solve for two unknowns. The two unknowns, namely, are the force FB and force FD. So here's our free body diagram, and here are appropriate scalar equation of equilibrium equations that we can use. And so we've taken, force to the right to be positive, force up to be positive. And so if you look at the first equation, if we sum forces in the horizontal direction, does FB have a horizontal component? Yes. How big is it? Well, all of FB times the cosine of 30 degrees. That's how big the horizontal component of FB is. What else has a horizontal component? Well, not FC. FC acts vertically, and so it does not appear in the sum of forces in the horizontal direction. FD, on the other hand, acts in the negative x direction, and so you see minus FD, but that's it. Only FB and FD have components, and in fact FD is all in the horizontal direction, but only those two have x components, so to speak. And so that sum must come to zero. Summing forces in the y direction, FB again has a contribution. It has a positive y component, and its magnitude is all of FB times the sine of 30 degrees, but then the weight acts downward, and so we subtract 392.4 newtons. And that's our second equation of equilibrium. Now you'll notice that FB and FD appear as separate variables in these two equations. You can't solve the sum of force in the x direction equation first. You got to solve the second one first, so the sum of force in y direction, so that you can get FB and then take FB, plug it into the sum of forces in the x direction equation, and thereby get FD. So solving the second equation gives you FB equals 785 newtons, and from the first equation you get 680 newtons for FD. Now, some situations require a little bit more knowledge than this. For example, springs can certainly apply force. Well, how much force? Well, it depends on their deflection. Most of the time in this class, we assume that bodies do not deform. They don't change their size. Springs are an exception to that. And the reason for that is because we can use a linear spring equation. In other words, an equation that says that the force in the spring is equal to some spring constant, K, times the deformation of the spring. Hopefully you've seen this before. Basically what it means is if you take a spring that's at its rest position, L naught, and you compress it an inch, you'll get a certain amount of force. You compress it 2 inches, you'll get twice as much force out of it. That's all this really says, is that the force that the spring applies depends on how far you perturb its length from its equilibrium or free length, L naught. Now cables, how do you deal with cables and pulleys? Well, cables are always in tension. You can't push a rope, so to speak. But what we assume is that we have frictionless pulleys and cables, at least most of the time. Later on we'll change that, and we'll consider what happens when we do have friction in a pulley. But for now, we're going to say that since the pulley is frictionless and it can rotate, the tension on each side of a rope or a cable will simply be equal. And so that's something you should know for making free body diagrams associated with cables and pulleys. As I said, cables and ropes and so forth can only support a tensile force, not a compressive force. And of course, that force acts in the direction of the cable. Now, what if we have smooth contact? What do I mean by smooth contact? Well, just imagine that this incline is made of ice. Okay, so there can't be any friction. Can there be any force between the incline and this weight that's being held up by some, tension from a rope? Actually, there can be. If the weight sits on a smooth surface, the only thing there cannot be is force up the incline. In other words, a frictional force. However, there can be a so-called normal force, a force that is perpendicular to the surface itself and acts through the, weight or wheel or whatever this thing is. Now notice that all of the forces applied to this particular body, this free body, act through the center of it. And so we can pretend that this body is a particle. And you notice that the normal force is force that the ramp applies to the weight in order to help support it. The tension T is from the rope or cable attached to the top of the the body. And then, of course, the body has some weight, W, that acts directly downward. Students get confused when they see a body on an incline and they think that somehow the weight magically changes its direction and now is perpendicular to the surface. That doesn't make any sense. Gravity acts straight down. And so we're assuming that this is a, the horizontal line and the plane is inclined at 30 degrees from a fair horizontal line. So the weight has to act directly downward, but the normal force is what changes angle. And the reason that happens is because the only force that the incline can apply to the body is a force that has no friction, and that is a so-called normal force. Now, why we use so many different words for the same thing, I don't know. If you want to say perpendicular force, that's okay with me. But we usually call it a normal force, and normal simply means perpendicular. Two words for the same thing. Now, again, we can assume or treat this body, even though it has some size, we can treat it as a particle since all three of those forces act through the center of that body.